Hello guys, welcome back to my channel Gamma Di Gamma. Apologies for the break again. I've been really inconsistent, but I'm always here. Don't worry, I'm not gonna disappear off the face of the earth. I'm back in the US for my spring semester, and I have a nice introduction to a very important topic that I have to offer. This is a formal introduction, somewhat formal introduction to Fourier series. And more than Fourier series, this video is all about the motivation, the physical motivation, the motivation in physics to actually consider something like the Fourier series. I mean, first they introduce how to represent functions as in terms of sines and cosines. But that seems arbitrary. Why would anyone on the face of the earth want to do that? Well, here's why. Let me spend a few minutes to describe the setup, which is really important in this case. We have our axes x and y, and we have some string. So we have some string, let's say n mobile beads on it, which means the 0th bead and the n plus first bead are basically the fixed endpoints, and we're going to impose those boundary conditions a little later. But there are n mobile beads that are basically moving up and down. So this is the beads on a string problem. We need to find equations of motion, specifically motion in the y direction. The string is this white line. Now all that matters is that the line passes through this red dot. I'm going to call this point p minus 1 because that's how I'm indexing it. This is p and that's p plus 1. So all that matters is this white string passes through all of these points, and what matters is that it has this linear approximation. It's basically roughly a straight line for this interval, this window L. That's, I've demarcated that with this extending red arrow. And it can curve both sides. All we care about, apart from string passing through the points, is you see this line here. I will emphasize a little bit. This is like the extension of the tangent of the line at when it is at the window L. So remember, we had a linear approximation at L. I mean, that's what is going to make all of this work. That's how we're going to introduce some differentials. Well, it's sort of an extension of that slope in both directions, and that's going to help us define these angles, because that's going to act like you need sort of two segments to define the angle. One segment is the x-axis, the other segment is this extension, this green extension. Okay, so far so good. I don't think there should be any problem. I've defined angles, and not all of them are same. I mean, in general, none of them are same, and that we're going to use this to our advantage. Also note that there is a tension acting. So it's acting that way, tension up and tension down. And the effects of these tension are what are going to help or drive the motion of bead P. So the force in the x direction, we can write the components. So there's a cosine theta in this direction, T cosine theta of P plus 1. Or let's think about it this way. Let's first write what's directly happening at point P. So say we take the tension here, forget that point. We don't really care about this part. Tension here, a sort of extension of that tension there. So you see we have T cosine theta sub P, you resolve it, minus, you resolve this down here. You can use some interior alternating angles argument to get a theta sub p minus 1 there. So we have t cosine theta sub p minus 1. Forget I talked about tension on the upper part. That's kind of irrelevant because, p is basically our reference point. So I'll just adjust a few things here. Okay, so now what we can do is we can pull out a first order approximation for this. 1 minus theta sub p squared over 2 and like other factors. Now, since I said we cared about first order, ignore this, ignore that. So if t minus t, which is 0. So, and again, we weren't really concerned about force in the x direction because the motion that's really interesting to this system is the motion along y. So force along y, I can do a similar approach. I have t sine this time. If you do trigonometry, you want this vertical component, theta sub p minus t sine theta sub p minus 1. So theta sub p, we know this is L, and we know the y is yp minus y sub p plus 1 minus y sub p. So we can use that. You can do trigonometry on this triangle. Y sub p plus 1 minus y sub p over L, the hypotenuse, minus y sub p minus y sub p minus 1 over L, which we can simplify. And remember, force is mass times acceleration in the y, so we can pull the mass down and have an ml. So we now have a second derivative of yp with respect to time, because this was motion for the pth bead. We can pull out another negative and then rearrange these. 2yp minus y sub p minus 1 minus y sub p plus 1. This is your equation of motion. And now what we're going to do is what we commonly do in physics. We're going to guess a solution. Some amplitude. This exponential term, because exponential is the eigenfunction for a differential operator, at least in most cases that we're concerned with. So if you plug this in, this simplifies nicely. And of course, this is for yp. Yp minus 1 will have just ap minus 1, the corresponding amplitude. So taking that into account, we have a situation like this. I'm just simplifying the algebra real quick for you guys. Now we need to impose the boundary conditions that the zeroth bead and the n plus first bead are fixed points, which means amplitude of the zeroth bead is 0. Amplitude of the n plus first bead is 0. Okay, we have a sub p plus 1 plus a sub p minus 1 divided by ap equals 2 omega naught squared minus omega squared divided by omega naught squared, where I'm defining the natural frequency omega naught squared to be t over ml. This is just some convenience. Okay, fair enough. Notice one thing, this is independent of p. The right hand side is independent of p. Now, this wasn't really obvious at all. But one way of achieving this, one way of determining what functions these amplitudes should be, is to guess that there should be some constant times sine or cosine, let's pick sine for now, of p times alpha, where alpha is some angle we don't know. And now if we try to compute the sum on top, we have c sine of p plus 1 alpha, I believe, sine of p minus 1 alpha, and we use the identity of sine A plus sine B. So that's 2 times sine of A plus B over 2, that's just P alpha. Cosine of A minus B over 2, that's just simple alpha. And notice what C times sine of P alpha was, that's just AP, right? So 2 times AP times cos alpha. So we divide both sides by AP. We have A sub P plus 1 plus A sub P minus 1 divided by A sub P equals 2 times cosine of alpha. And indeed, this part is really independent of P. So this was a clever observation. If you study trigonometry enough, it might become obvious to you, but it's really hard. And now we can impose boundary conditions. A sub 0 is 0. And we had this form. So if you plug in 0 in place of P, this is just trivially true because sine of 0 is 0. So that doesn't really help us. A sub n plus 1, so that's C times sine n plus 1 alpha equals 0, which means alpha times n plus 1 equals n pi, where n is some integer. This is just the general solution for the sine. So that means alpha is generally n pi over n plus 1. So we have like an n amount of them which sort of satisfy these conditions. So more generally, the amplitude of the pth bead, nth mode of that, so each integer n generates a different mode. C times sine of P times n pi or capital N plus 1, where n is like the number of mobile beads. This is the nth mode of the amplitude of the pth bead in this. So if you remember what our guess was, it was the amplitude times the time oscillating part. So this just means we have C times e to the negative I omega t sine of P n pi over n plus 1, but we still don't know what omega really is. But I mean, this formula is useful then. We can use this formula because this structure is just equal to this. This is a more crude way of doing the eigenvalue eigenvector analysis that we usually do for the coupled oscillators or whatever. But you can see from this, we can solve for omega to actually get, let me just simplify algebra. 4 times omega squared sine squared of n pi over 2 times n plus 1. This is just simplifying the algebra altogether. These are the mode frequencies. So you keep changing the n. So if you have n equals 1, that's the first mode, n equals to second mode, and vice versa, because n is an integer. So these are the mode frequencies. And we have the mode amplitudes as well, or just the modes. So these guys go hand in hand and actually help us generate. We just have a subscript n maybe, so could have maybe started with that, but it doesn't matter because we can sum over them. It's a linear combination. So more generally, this looks like some constant which we determine based on initial conditions because we solve for the boundary conditions. Sine, I'm choosing the cosine part of the e to the I. I'm just assuming something and adding a phase factor to account for the what if there was a sign instead of what if we chose a sign. I'm just accounting that with this phase factor. Sine of Pn pi over n plus 1, and if you want we can like sum over them. I'm just not writing it. So this is what we call the initial waveform, because at say if you plug time equals 0, the initial, this cosine will just be a cosine phi, which is just a constant. So we just have a c prime, and then this part will remain intact. So this just tells us what the wave looks like before, it's before time begins, or before like any other oscillations can start. Because all the e to the I omega t, or this exponential or this cosine part is going to do is just going to evolve it. It's just gonna make it go back and forth. It's just gonna make it oscillate about those fixed points. Of course, we can have different frequencies because depending on the modes, but that's what this time part is gonna do. So this initial waveform is what matters. So I mean, I should have probably marked it here. This is the envelope. It's what's giving this, the form that the time part will have to work with. The time part just oscillates. It doesn't change it drastically. I mean, that's the way we constructed our solution. This is a more direct observation of a solution which looks like it's got distinct spatial and temporal parts. So it's a separation of variables going on without us even assuming that the solution like this existed. Now the question is, I mean, this was a more crude scenario with like p discrete beads on a string. What if we create a continuum? What if we shrink this L to something like delta x, where this is really small, so this is going to 0. What if we like shrink the distance between individual beads to be infinitesimal? And that's when we're going to have a mass distribution on a string. So we're going to have a string like we have, say, for like a guitar or a violin, which has mass. Because here the string we assume to be massless. The only thing that mattered was the beads. And now after we do this sort of continuum limit, that's where we can try to derive the wave equation. This is not a general derivation. General derivation just directly works with a string like this. But this is beautiful in the sense it gives us the motivation for Fourier series. So let me just briefly go over some of this continuum approximation, continuum limit. So x equals PL. Let's just define x this way, because if you look at the argument in there, we have this, which you can set to be x over L, n pi over n plus 1. So there's like n plus 1 components, although the 0th and the n plus first are fixed. So there's total like n plus 1 real components anyways. So L is like the length between like any two beads. If you multiply the small l and assume a uniform distancing between all of them, you get the total length of the string for L times capital N plus 1. So we're going to be working with this. So our solution, so y sub p of t, instead of indexing discretely for each bead, once we do the continuum limit, we're going to have x. So we're going to have beads at every real number, because x is like in real numbers, in the domain of real numbers. There's no s there, my bad. So there's beads at every real number. So it's a function of x and t. And our solution, we should expect to look like cosine omega t plus phi sine of n pi x over L. So this is what our solution should look like. But the differential equation really matters, because that's is a more general thing than one solution which is subject to boundary conditions and initial conditions. So y sub p plus 1 of t, using a similar analogy, is going to be x plus delta x, because remember the distance between the bead, I made them delta x. Similarly, y sub p minus 1 of t is just going to be y of x minus delta x comma t. And now we can just put this in for equation. Second derivative of y sub p But we can write this as a, we have to do a partial derivative because y is now a function of x and t of y with respect to t. So that's two derivatives there. Negative t over ml. And you see the factor we have here. Let's just write this out for our convenience as yp minus y sub p minus 1 plus yp minus y sub p plus 1. Because now we can like sort of use some properties. So we have yp, that's just y, minus y sub p plus 1, which we can Taylor expand clearly to be y plus partial y with respect to x delta x 1/2 second derivative. Let's do a second order approximation. Similarly here, y minus partial derivative dx 1/2 second derivative. No, it should be partial delta. So we have y minus yp minus 1. So yp minus 1 is like this guy. So this becomes a plus and a minus 1/2. And there's another y minus p plus 1, I believe. Yeah, I keep forgetting. So we have just another y, first derivative term, second derivative term, and then close it up. This cancels with that, this cancels with that. First derivatives will vanish. The second derivatives surprisingly add up. So, that made sense to do a second order approximation. T over ml. You know what? I would just like to change ml to this delta x because that's what we defined on top. And we have suck in the negative. Half goes away because they're adding up. Delta x squared. So one of them will disappear. We have a second derivative in time. And t over m divided by delta x. Now this m divided by delta x, although delta x is like the hypotenuse in this case, if we do a continuum limit, this angle becomes really small. So delta x, or this L, this hypotenuse actually just becomes the horizontal because of the small angle. So this m over delta x, we can call it the linear mass density rho. So our equation just looks like P over rho. And all of this is just equal to the second time derivative according to Newton's law. And there we have it. This is our wave equation. So you see, we did all of these sort of cheap approximations and limits for the continuum, going from the beads to this continuous case where we now have a string that's vibrating. And of course, we also converted the solution by direct analogy. Of course, you can solve this and you would get something like this. So we aren't truly that mistaken, but this is not the most general derivation you would find anywhere. This is nice because, as I said, our solution looks like this. Again, assuming the cosine or the real part of the oscillating exponential, right? The initial waveform is, well, cosine phi is another constant, so a naught, sine of n pi x over L, this looks something like this. But if you want to talk more generally, the solution looks like we're going to have either a cosine or a sine, which we actually accounted with the phase. And we may not even have a sine here. This sine was according to the boundary conditions. What if we have a cosine and a sine? And again, since the system is linear, we can have a linear combination of them. Each of them, both the time parts and the position parts. But again, as I was saying, initially, we're just going to have a combination of these cosine parts and these sine parts. But now here's the problem. Here's the problem. Assuming we set the initial conditions, what if we have a problem where we're actually plucking a guitar now? So we have something like this. This is the horizontal. We pluck the guitar initially like this weird shape. We like pluck it here. And then just leave it so that, after leaving it, then the time part kicks in and it starts like oscillating with, of course, the given modes that are permissible in this boundary value problem. But again, I said the solution has a linear combination of sines and cosines, but we have, this is an arbitrary function. I mean, if we plucked it like a sine with some frequency or some, in this case, wavelength, if you want to think about it that way, or even some like cosine, but cosine really isn't possible given the boundary conditions. I'm just writing this for generality. Then all we would have done is just like found like the weighting constant. So if there's like 2, our constant in front of the sine would have been 2, and then initial part is like 2 times sine of whatever wavelength times x, and then we're done, and just multiply the time part and then we're done. But what if we pluck it in like a weird manner that's not a sine or a cosine? So we have some arbitrary function, but we know each solution it'll be easier to work with this problem or find a solution if we can express this as a sine or cosine, because then we just find the coefficient and then just multiply the time part. Find the coefficient for the linear combination, just multiply time part, and then you're done. So the problem of the initial waveform just looks like this. Assuming we have to find some combination, some linear combination, it could be infinite also. Depends on how crazy this function is. On this interval from say 0 to L, or minus L over 2 to L over 2, that's probably a better way of thinking about it. They have to add up to L because that was the length of our string. Plus Bn times sine n pi over Lx plus the cosine 0 factor. So let's just call it a naught over 2. So we need to find these coefficients so that after we find them, we can represent this arbitrary pluck as a linear combination of sine and cosines because we found the coefficients. And then to find the general time dependent solution, or just the general solution depending on position and time, just multiply by the appropriate cosine omega t plus the phase factor, and then you're done. So once we figure this out, once we figure these weighting factors out, no matter what pluck you give me, I can always find these weighting factors, assuming we can find a good method. Just multiply by the time part. Like this. And then you're done. That's your solution for this wave problem, this string oscillation problem. And this is your formal motivation, or not so formal motivation, given how sleazy the derivation was initially, for Fourier series. So the idea, this is a Fourier series expansion of f of x on this interval L. 0 to L or minus L over 2 to L over 2. It should all add up to L. The way of the regime where we find these coefficients by orthogonality, which I will sort of maybe, we don't have time, maybe in the next video after I recap. The regime of finding these coefficients For the what will permit us to expand a function on some interval of periodicity is basically what we do in a Fourier series. All we do is find these coefficients and then expand the function, because after we do that, after we represent this as a linear combination of sines and cosines, we can be proud with our head held high. Just multiply this cosine omega t plus phi factor to generate the solution, and then you're done. Because every solution, at least for the boundary problem, value problem, and the initial conditions we've defined, looks like this. So we find the weighting factors, and it makes sense with summing because there's different modes for all of these. Same goes with the frequencies actually. So to think about it, there could actually be two independent sums if you want to actually sum and account for all the different modes. Again, an infinite sum, because there's an infinite number of integers. N is an integer. So I think this sort of gives you an idea. I will talk more in the next video. Please like, share, and subscribe to my channel. Recommend your friends. Stay tuned for more. I will be back because this sort of, we've just we've kindled a spark which will ignite a flame. So for igniting the flame and, burning firecrackers with it, we still need the next video. So see you there.